Hello, welcome. All right. I think I need to ping some people. Give me just a second. All right. Awesome. While people are hopping in, I'll do a quick overview on the agenda for today. I'll keep it brief. We're going to be kicking off with um, Okay, we're going to be kicking off with AIP 107, new loader and code cache for MoveVM. Our presenter will be George, moderated by Igor, and then we'll transition over to Oliver to present about AIP 108, enabling interoperability for federated keyless accounts. And Owen will be moderating for us there. All right, so to make sure everyone is ready, let me check if George is here and ready to present. Let me see.
Yeah, I'm here.
All right, cool. All right, I'll let you kick it off.
All right, let me share slides. Can everyone see my screen? I think this is a yes. I guess. Okay, anyway, I guess I can just start that. Okay, cheers. So I will not see any messages in the chat. So if you have any questions, maybe feel free to interrupt me, or you can also try to leave the questions until the end. Like same goes about the hands. I probably will not see them. Anyway, so my name is George. I'm with the VM team at Aptos, and today we'll be presenting AP 107, which basically going to talk about the new loader and code cache for MoveVM. And first of all, I just want to get everyone on the same page and talk about what MoveVM is, what is a code cache, and what is a loader. So essentially, VM is just an interpreter which executes certain move bytecode, which is stored in units called modules. And these modules are cached for performance reasons. And currently MoveVM owns this module cache, so it stores it kind of inside its instance. And then MoveVM uses a structure called loader, which basically just a helper thing that helps you to get these modules from the cache. And if they're not found in the cache, it will go back to storage, to the state, deserialize modules, verify them, and then cache them. We also have Aptos VM, which is a wrapper around MoveVM, and basically it's an execution unit for a single transaction. In Aptos VM, you can also publish code, and like the way it works, you have some like code publishing transaction, you submit it, right, and then the modules appear on chain after. There's also a feature where you can initialize the state straight away when you try to publish some code using the resources defined in the code that you're publishing for the first time, called init module. And importantly, when you publish the code for the first time, this init module essentially loads this newly published modules into the cache of MoveVM. Finally, like moving higher up the stack, we have BlockSTM, which basically operates on blocks of transactions. It executes blocks of transactions concurrently using multiple threads. And in essence, each thread owns a kind of Aptos VM instance, like essentially having this thread local module cache and execute transactions speculatively. So the transactions, even though they're ordered by consensus, they executed out of order and speculatively, and therefore potentially we can identify that, well, there was a read-write conflict, so we missed speculation was incorrect, so we need to abort transaction and re-execute. That's kind of the background. So now let's look at the existing problem with VM and its caches and loader. So firstly, the existing code is kind of like very spaghetti and doesn't really have well-defined semantics. So it's really implementation based. The code is really fragile and hard to understand. I'm sure like people who looked at loaders code, if there are like some of those people in this call, they would understand the pains. And essentially it makes non-maintainable, fragile, also worsen developer experience and user experience, and can be source of any sort of bugs in the future. The second problem is that the existing VM is simply not thread safe, right? So we kind of have on the BlockSTM side, we use a VM per thread because of that. Is there a question?
Or maybe if you want to sit next to you, but you plan it.
I guess it's just Alex, if you can mute yourself. All right. So basically, BlockSTM uses a VM per thread, which means that we have like this thread local caches essentially. And then this also leads to sort of interesting problems and in the end performance regressions, because whenever you call this init module on modules that are being published, these published modules are not yet committed to chain. So it's possible to run this init module, cache this load the modules to put them into the cache, and then you realize that transaction runs out of gas, and then the module is not committed. But the cache has a populated entry for the specific module, right? So you basically get an inconsistency. The same thing applies to block STM speculation. When it executes stuff concurrently, it's possible to have a transaction which publishes module, other transaction reads this module. The first transaction that published modules actually aborts, and you end up with a state where there is a VM instance which actually cached something which is not actually published on chain, right? Which is really bad. So it's not a security issue because, well, there is a solution. You just like flash caches, you fall back to slow execution mode, but it hurts performance, right? And this is really problematic. And then finally, kind of the existing design is that the cache lives inside the VM. So in essence, the lifetime of the cache is tied to the VM. So it's not possible currently to cache modules across multiple blocks. And whenever you start executing a new block of transactions, you basically need to load everything from scratch, right? You can do some prefetching, which we do, but not for everything, right? You don't know what's going to be accessed in the block straight away. So the goal of this AIP is to kind of address these three problems of poor reliability, bad performance, and not being able to cache blocks for longer. And the proposal to kind of redesign the architecture, move VM, and the code caches to make sure that we can actually improve on all of these three axes. So in high-level summary, basically what we're doing is we changing the MoveVM APIs to make sure that the module cache is stored outside, right? Essentially, we make the VM stateless, and therefore, by tweaking a few data structure there as well, we can make it thread safe. So essentially, you can reuse MoveVM concurrently without like all these weird cases with module caches. And important, it also allows to implement custom code caching logic outside by clients that want to use MoveVM, right? It's not just us, Aptos using MoveVM. There are also Movement, there is Initiate, and so on. And like, for example, I've been talking to some of Initiate developers, also had these issues where you try to publish modules, it ends up in a cache, and then later you kind of want to roll back, but you have no control, so you need to flush the caches, and it hurts performance, right? And then the second important part of our design is that we want to improve performance. We want to avoid this flushing of cache and like this fallbacks to kind of slow pass execution mode in block STM. And we do this by changing block STM algorithm to work with module publishing correctly without this kind of speculation, which I'll describe basically in a second. And we'll also introduce global module caches to make sure that our performance is even better, that we don't basically have cold starts at each block. What is out of scope is many different optimizations, which we could have done, but we don't want to do. But potentially we'll do maybe in the future. There are like you can optimize the way you access modules, you can optimize the way you try to access dependencies, you can use some unsafe Rust, arena-based memory allocations. We don't really consider this. We care about just like kind of laying out the base infrastructure, which we can use as a baseline with decent performance. And after that, there can be multiple improvements on top, and also contributions are welcome. In terms of timeline, so the feature is completely implemented, PRs are merged, and like the whole thing is included in 1.24 release. And the feature has been enabled on DevNet and testnet. So it's been running for some time already. And ideally, we wish to be able to enable it on mainnet soon as well to get some nice performance speed up. All right. So the solution I'm presenting here is essentially we removing the code cache from MoveVM. And essentially, instead of like hard coding the caching logic inside the VM, we want to make sure that VM is generic and it talks to the cache through traits. So essentially, I think you can look into the actual AIP for more details about what the APIs look like, but you can think about it like this abstract trait where you have a way of accessing modules from the VM generically, and then the caching is completely orthogonal to you, right? You don't like when you fetch a deserialized module, you don't know what the cache will do. Maybe it will cache something, maybe not. It's up to the clients who implement that, right? And this basically allows us to kind of nicely make the VM generic, make sure we have some basic module cache implementations which people can use, right? But also make sure that it's fully customizable. And then finally, we want to make sure that there is no speculative caching. So like whenever you try to publish a module, it's never cached. Like no speculative information is cached. Like only when you commit module to on-chain state, you want to put it in the cache. right? And the idea is basically to kind of change the way module publishing works in MoveVM, the technicality of which I'll describe later, by never caching modules when you publish them. So even init module will not cache anything, right? And this solves this problem of speculatively caching some unpublished code. And then similarly for BlockSTM, we tweak the algorithm, which on a high level basically ensures that whenever you run transactions out of order speculatively, you don't modify the cache, so it stays kind of intact. And only when you 100% sure that transaction is ready to be committed, it will not be re-executed anymore. Only then you make this kind of module that are being published visible to the outer world, and then some other transactions can basically see that, oh, there was some publish, and potentially re-execute and reread the state. But this basically solved the problem of caching speculative results in BlockSTM. And yes, like lastly, because we want to have the global caches in this recommended solution, we propose to have a two-tier kind of thread shared cache system, where essentially you have a kind of a cache maintained by BlockSTM, to which you put modules which are not yet cached, and where you also put the modules that are being published, kind of like this kind of a like heavy arena where you kind of like synchronize accesses, make sure it's like not be like synchronized, so you also pay the price for accesses because you need to acquire locks and so on, right? And also have the global module cache, which is lock-free, where basically we want to make sure that most of the modules are basically live in this cache, and then when this module publishing, which is rare, happens, you put them in this L2 kind of BlockSTM cache and read it from there, and then you can migrate it to the global cache. Speaking of alternative solutions, I mean, there are none really, because, well, to make the VM thread safe and kind of usable and extensible, you need to move the cache out, right? As long as you provide certain APIs for other MoveVM users to be able to kind of do whatever they want, right? You really need the cache out. So now we can dive a bit into technical specifications before I go into like details about compatibility of this feature and performance and testing. So as I said before, MoveVM just simply interacts with any kind of caches through traits, and the caching behavior is completely hidden. So for example, if we consider just a single MoveVM instance and you have some like user-defined modules like type that implement this module storage trait, and this line that goes from left to right essentially represents execution time. When you execute bytecode instructions, what can happen? You can basically dispatch calls to this module storage, and then the caching behavior is completely orthogonal. So for example, you can check for existence, and then this existence would just cache bytes. Then you would maybe try to fetch a deserialized module later in the time, and then you would go to cache and then convert this byte representation into compiled kind of deserialized representation. And then later you can also try to fetch a verified module. And at that point, you would also run a move bytecode verifier and make sure that at that point, like this, the cache contains the verified code, right? And essentially what we kind of implemented so far, like represents what I'm describing here, where like you can read full details on the AIP, but you can have like different states of modules which are being cached, and it's fully implementation like like MoveVM doesn't really care about anything, so it can be basically swapped whenever we decide to change module storage. It's easily extensible and changeable. Finally, as I said before, we want to make sure that MoveVM never stores published modules. So before it was done in the following way, where whenever you try to publish modules, you would put them in the cache, right? But then there was also kind of a write set that transaction would produce. We just make sure that MoveVM doesn't cache anything, right? Right now it's stateless. Essentially, MoveVM, the only thing it does, it just verifies if modules can be published given some state. And if they can be published, then it's up to the user MoveVM to decide what to do with these modules. If they want to cache them, if they want to synchronize caches, evict something, it's completely up to them. But MoveVM doesn't have any state, so nothing gets cached, right? And it's very important because it allows us not to cache any speculative information and makes the VM thread safe. Finally, moving to more fun parts, we have to change BlockSTM algorithm, because essentially BlockSTM algorithm is the algorithm which would run MoveVM concurrently, right? And it would basically need to deal with this cache synchronization when modules get published. So as a refresher, how how does it work within block STM when you execute a single transaction, like a block of transactions, but like for one specific transaction. So in terms of life cycle, there are kind of like three main stages. So all transactions are executed out of order. And like when one transaction instance is being executed, we record whatever it reads as a read set, and also whatever it writes, like it's produced as a write set, right? And then whenever like a write set is produced, you make sure that higher index transactions are being revalidated, right? Essentially, if you execute transaction 10 before transaction 1 out of order, you need to make sure that if transaction 10 writes something, you check if transaction 1 has read something that transaction 10 had written, right? And this is basically the part called validation, when we want to make sure that if, like, whenever transaction has a read set after execution, we want to reread it again based on the current state, which potentially have changed, and want to make sure it's the same, right? If it's different, it means that some transaction had written something, so you want to re-execute. And then finally, there is also kind of a commit stage, where at some point you realize that, well, all preceding transactions can be committed. They will not be re-executed. So whatever writes that you produced is no longer speculative. You cannot be aborted, essentially. And for regular, like in general, for transactions, it's kind of a no-op. We just, at some point, we know, but there's nothing interesting happens. So how do we change it for modules? So for modules, we kind of do it in the following way. So first, we still record the read set for modules the same way we do it for any other values. But importantly, we don't produce a write set. And again, the rationale is that after execution, transaction can still be aborted and re-executed again and again and again. So you want to make sure that, well, transactions don't run on top of some speculative state, right? So they don't even see these writes. Validation works exactly the same way, but what is important is commit. Essentially, when we know that transaction is ready to be committed and it's no longer going to be re-executed, we make the writes that transaction makes for modules visible to other transactions, which essentially means that transactions which are kind of ordered above but may have executed before, they get revalidated, and they will see the new changes done to the state, and they will be essentially re-executed and execute on top of a correct state. So we have this kind of rolling commit of modules in essence. Finally, I'm just kind of talking about abstractly how modules are being read, right? But what it actually means is, like, we have this multiple tier caching system where essentially each transaction holds its own per transaction cache. If module is not found there, we go to global cache. If it's not there, we go to this per block cache that block STM is managing, where it puts committed modules and modules found then later in storage. And if it's not in per block cache, you go all the way down to the storage, to the DB, and get the bytes from there. And importantly, on cache misses, you would copy the modules into this per transaction cache to make sure that whenever transaction runs, multiple runs of the same transaction will get consistent results. And basically, this allows us to integrate global module caching through block STM, right? So essentially, the hope is that most of the modules will be in the global cache, so have nice log-free accesses to global cache. And then if it's a cache miss, then we go to kind of like more heavy synchronized block caches, which have slightly higher latencies. All right, so this kind of concludes the technical part. So I'm just going to go through the risks associated with the AIP, performance testing, and so on. So obviously, it's a big change from MoveVM. Aptos VM, block STM, the whole stack. So there are certain security considerations, which we'll touch upon a bit later. But obviously, like, the goal is to minimize those, and we try to do it by not just testing, but like also making sure that everything is feature gated, and that the implementation is mostly done in the new files instead of like changing the existing code, to make sure the reviews are easy, like components are versioned. So we make sure that the old path is still like almost the same, right? And it's only the new path that needs to be reviewed and checked. What is the risks and security concerns? Well, obviously, like, feature gating might not be complete. We try to do so. I mean, hopefully it is. Also, like, certain variants might not hold. Again, we prefer, instead of expects and panics in Rust, we prefer errors to make sure that, like, the node just doesn't crash. Because we're sharing VM across multiple threads, there are potential of deadlocks, so we need to audit the code carefully. And then finally, because BlockSTM runs transactions concurrently, there can be non-determinism bugs. Again, we're trying to make sure that this doesn't happen. But we need to be aware of this. Coming back to testing, we want to make sure that whatever I present, like the risks I presented before, these problems don't show up. So I have a bunch of end-to-end tests implemented. We also have some.
Just to do a time check, we have like 8 minutes. Do you want to see if there are more questions before you go here, or you want to kind of quickly go here before we see?
I have like 2-3 minutes, I think, left, so I can just quickly finish stuff and then open for questions. So far, no one interrupted me, so I guess there are no questions. Yeah, so basically, I have some good testing coverage, which obviously can be like it's non-exhaustive, so always can be improved. But the feature is running on dev-netted testnets, and like so far, the results were good. Finally, performance. That's kind of the most important outcome of this project, right? Like, wanted to also improve the performance of the VM. On synthetic benchmarks, we have some nice speedups for blocks where there is module publishing. When there are like lots of modules being loaded and accessed, we also get some nice speedups. Is there is high contention? There are like a bit of regression, mostly due to like, again, like the synchronization overheads potentially, but we're still investigating. But importantly, like it's how this plays out on the realistic workloads. And for those, we basically have a set of kind of benchmarks which try to replay the workloads using the same set of transactions that run on mainnet as if new loader was enabled there. And we get some nice speedups. And then we'll also run some benchmarks on the real network, where on one of the nodes we enabled the feature. On the rest of the nodes, it was basically the old implementation. And on the bottom line, like here, you can see the block execution time, average block execution time, and you can see that whenever the new feature is used and enabled, it goes down significantly, which is a great result. And then there's some load testing that we still need to do. Finally, before I conclude, I want to talk about backwards compatibility and ecosystem impact. So the new implementation is almost fully backwards compatible. Like it's very unlikely that there will be differences, but the behavior is still different. So like when we replayed transactions, we found that there are like a few expected divergences, mostly due to weird behavior of existing infrastructure. I added a link here, and there is a link on AIP, so you can check what exactly it is, like what is the divergences. But like essentially, it's very stupid stuff. Sometimes like no error message in the old implementation, new implementation does find an error message. So basically, kind of enhance on user experience with these divergences. This does impact kind of compatibility, right? We want to make sure that most of the nodes are upgraded to 124 before we can enable this feature. And obviously this can impact whenever we roll out, that simulation results on non-upgraded full nodes can be different from the actual execution. So something to be aware of. There are lots of future potential. We can remove old code. We can improve performance even further and reduce gas costs potentially, because right now there is gas being charged for dependencies. We can actually improve this and reduce costs for the users, which would be great. So with this, I want to conclude and open for questions. I've seen there are like some messages in the chat, which I haven't seen yet. But basically, we make the VM move. With this API, move VM becomes thread safe. It becomes stateless. The code caches are moved out, and the users of move VM implement them. And then there is no speculative caching anymore. On Aptos side, in BlockSTM, we implemented the code caching logic, making sure that in parallel you can publish modules and without falling back to the slow path, right? And cache flashing, we have a lock-free global module cache, and this allows us to get some nice performance benefits and opens the way to kind of future optimizations. So with this, I conclude. In terms of like what's next, we like appreciate any feedback, any feature requests, and hopefully we can discuss and enable new loader on mainnet soon. And again, MoveVM is completely open source. If you have any feature requests, you see some weird behavior of VM, or you want to, I don't know, like try to make it more extensible, reach out. We can work together on this. And some references for people who are interested. There's a pull requests implementing the feature, AIP, and that discussion. Thanks.
Yeah, that's some stellar work. I was going to ask if it's possible to get a copy of this slide presentation, because I was wondering if I can grab those links for the pull requests.
Yeah, I think it should be possible. Yeah, we can share.
Okay. All right. Thanks.
Also, they should already be in the AIP, so if not,
Okay.
we'll add them there.
I'll take a look at the repo. Thanks.
Yeah, I think at least like 3 links in a bold are definitely in AIP. Like non-bold links are basically kind of a very small pull requests, which are not really relevant to the actual implementation, just kind of nits. But I'll update AIP for completeness.
Awesome. Any other questions or thoughts from folks?
I had a question about replaying. You mentioned that when you replayed the transactions, like in a testnet environment or DevNet, what were you looking for? Anything in like thrown error, any kind of thrown errors? How do you kind of sort out with all of the blocks? How do you sort out like what to look at as far as backwards compatibility? Is that's all in the testing?
Yeah. So basically, so there were so basically you can replay transaction, right? Like all the way from Genesis. So like on our own testing site, we have jobs which allow you to replay from like version A to version B. So I think like currently there was a range from like not from Genesis, but like basically it's sometime close to Genesis from which we replayed like lots of transactions. And then I basically had to manually scan over them. So hopefully there were like no big difference. Like there were only a few differences, right? Because it's kind of difficult to categorize because errors sometimes like really unexpected, right? So we basically kind of need to see the execution trace to make sure that like what you suspect is happening is actually happening. Because like, for example, you see the gas usage is different. How do you know what actually had happened, right? So basically I had to trace, like with the gas profilers that we have, I had to trace the execution to see that, well, now init module runs with previous loader init module, like erroneously didn't run. That's the divergence. That's why there is a gas difference.
Cool. Wow. Yeah,
but yeah, like
at a high level, the replay will basically mark out any transactions that produce different result with the new change and with enabling it versus the baseline at that time. So only transactions that are different, then we kind of look manually and then try to understand why.
Yeah, that's also hard to like reproduce the state of the chain, just by replaying, because you're not going to get the usage, right? It's going to be tough. I guess that's what the role of the profiler is, the gas profiler.
So the replay actually basically takes the state, basically for any individual transaction, there is an input that the transaction takes and outputs that it produces, and the replay will basically execute it with that state at that given time. So basically the replay of any individual transaction is equivalent to basically running a node at that time and rerunning it. So we do have all the information about transactions to be able to replay them with fidelity. So like in general, if we have changes that don't expect to have backward compatibility changes, like the replay confirms that everything produces the same output.
Nice. All right, thanks.
Cool. Any other thoughts or questions? There are also some, like this is really kind of exciting, and it's been kind of long in the works. And this will also open up some future endeavors like dynamic loading or lazy loading, or some other interesting things that might be coming, that George might be discussing in some of the future AIP sessions. So stay tuned.
Yeah, I really think this AIP is kind of understated. This is a really, really amazing change. So in case that's not clear for people on the call.
Yeah, and from the perf side, if you look at the kind of the graph, the majority of blocks that take a lot of time to execute today, like basically the blocks that are higher on the execution time are mostly because of the module loading. So basically this makes kind of those expensive blocks kind of are expensive blocks are improved much more than the rest. This makes things much more kind of predictable, and this also should kind of reduce the latency on the network a few tens of milliseconds as well. So because the execution is going to be shorter, so and more predictable. So yeah, once this is on mainnet, there might be some cool results that George might be able to share.
One question I have is, it seems in replays, sorry, you seem to only run it on like 200 transactions, like the interval there. Is there?
Yeah,
So-
that was for the performance.
This is for benchmarking. This is just like a random snippet. This is not the full replay. Like basically we have a replay which checks basically if given the inputs, the outputs are as expected, which is stored on chain. But we also have an infrastructure which allows you to basically replay blocks of transactions, historical transactions, with certain features basically being overridden or changed. So like for example, loader, like this new loader was not enabled before, but we can kind of forcefully enable it and just rerun those blocks, right? Because if it's fully compatible, then transactions would run faster, but without any divergences, right? And like for example, for this block, it's like 180 transactions. There are no divergences, but then the execution is significantly faster.
Okay, I see. And have you like ever noticed a slowdown on any replay? Like, is there a scenario where that happens in with real data that you have besides synthetic data?
So for replay, we kind of only manually selected like certain pieces of like chunks of transactions to kind of just randomly select the ones to kind of estimate whatever like what it would look like on the mainnet, but we haven't like really replayed end to end, right? Because like to actually benchmark, you need the multiple runs, and if you replay from Genesis, it will like take weeks. So we haven't done that. But yeah, like we had some regression on synthetic benchmarks whenever you like try to access the same module all over and over again with basically the same access pattern, which potentially may be due to false sharing or like some synchronization overheads, because like we use lots of like arcs and atomics in the code base, so that can be an issue.
Yeah, and the kind of for the other chart, you run this on the mainnet for a couple of hours, and there it was generally better for kind of across the average across all the blocks. So, but yeah, there might be some spikes where the single workload is kind of slightly slower. I think with the interest of time, unless there are kind of some other questions, we should head out to the second presentation.
All right. Awesome. Thank you so much, George and Igor. Up next, we have Oliver for enabling interoperability for federated keyless accounts. Oh, Oliver is not here.
I am here.
Oh, you are here. Oh, sorry. I didn't see you. I didn't see your
No,
awesome
sir.
blonde hair.
Oh, is it sharing?
Yep, it's sharing.
Okay. Right. Hello, I'm here presenting for AIP 108, which is really just an AIP about extending the product usability of one of our account features called federated keyless, which itself is an extension of our keyless authentication model. So to give a little bit of background information, what keyless does is it enables social login for OIDC providers, and currently on mainnet we support Google and Apple. In short, it allows for people to use the JWTs that are provided by these identity providers to authenticate into an on-chain account. There is a layer of ZK proofs that are leveraged to make sure that privacy is maintained. Sensitive information such as your email is preserved. Then on top of keyless, we built federated keyless, which allows for more customized authentication via certain IAM providers, identity management providers such as Auth0 or AWS Cognito. So for these JWT tokens, and a lot of this is in the design of keyless accounts. These accounts are generally scoped to the application and user. So for a given JWT, it's scoped by certain claims within the JWT, including the issuer, which kind of defines the identity provider, the odd, which defines the application, the sub, which defines the user. And so a given account isn't really portable across applications. And this is done by design because if you could access the same account across applications, for example, for like Google, then a certain malicious a malicious DApp could get a user to log in and then take whatever account malicious actions on the account, and then this account that is used across other applications as well are compromised. However, in the world of federated keyless and with these providers such as Auth0 and Cognito, there's a notion of a user pool or a tenant, and that's defined within their issuer. So most of these keyless accounts, the regular keyless accounts that are backed by Google or Apple, they have the same issuer, and thus if the accounts also need to be scoped to the application. However, in this case, in Auth0 and Cognito, the issuer is scoped to the customer of Auth0 itself. So to give an example, for example, a brand like Disney, perhaps that they want to share the same account, like they might have different sub-brands, such as ESPN or Pixar and something, and they are under the same kind of parent system, and they might want to use the same login or the same sort of account identity model. But because within how Auth0 and Cognito are set up, to be able to maintain these different brand identities, they'll have different applications. And since the odd claim within the JWT will be different, then there isn't an ability for these accounts to be interoperable, even though there is a sort of notion of trust as they operate within the same user pool and tenants system. So this AIP is really about allowing us to tweak the federated keyless model to be able to model such product use. So at a high level, the the solution isn't very complicated. So we have here the ZK relation, and this is there's a lot of variables here, and there's more details in the original keyless AIP, which will provide a lot of context about what keyless is, what is kind of going on here, and how that's leveraged. But here in the private section of the private inputs of the ZK relation, what we're going to do is add a Boolean flag here highlighted in red called skip odd check. And based off this, this will trigger a divergence in the logic of the proving path. The difference here is highlighted. These are the steps that are taken in the circuit that sort of enforce the keyless relation and does all the checks within the circuit. And so here in step 6, we're adding logic that's gated around the skip odd check, which in the case that it's false, then we do the normal thing that we used to do. But here, if it is true, then we check whether or not we're in this override odd mode. That's not really that's this whole kind of other mode that I won't kind of get into. But if the skip odd check is true, then yes. Yeah, if the skip odd check is not sure if it might need to be switched around, but if oh sorry, yeah, okay, it's the I'm not super familiar with the notation. If skip odd check is false, then we're gonna do the same thing that we are doing before. It just models the old version here, but in the else case where we do want to skip these the checking of the enforcement of the odd, then we will assert that the private input, the odd val that's being used as part of the address is equal to the empty string. And it won't do the enforcement of the check, which takes the JWT and asserts that the odd val here, odd val private input is equal to the odd val that is in the JWT. And in some of the earlier steps, the circuit goes through the steps of verifying the JWT signature and does some of these matching and does some of the matching. In terms of the actions required to support such a change, the main change as reflected in the prior slides is really in the circuit. We need to enable the ability to have an extra private input. And if it is disabled, we'll just do the status quo set of verifications. If it is enabled, then the circuit will use the empty string for the odd private input, which will then be used of the odd value committed in the ID commitment, which is inside the keyless public key, which is part of the public key, which defines the address of the account. And then the circuit will skip the logic that matches the value of the JWT odd value with the odd private input. On the prover side, it will need to be able to take an update for the API to know whether or not to trigger this private input to enable this oddless mode or not. And that'll be done by just adding a Boolean field to the request. Similarly to the pepper, which is, if you're not familiar with the pepper, that there's more details about it it's a separate AIP which defines a service which is used to preserve privacy for these keyless accounts. It's a sort of it's a piece of entropy that is created from the hash of certain claims within the JWT. And since the odd value is one of these inputs that goes into the hashing of the pepper, we need to also make sure that if we're in this oddless mode, that the same pepper is being used across applications. Otherwise, when this account is when this account is being trying to be accessed across different applications, if you don't use the same pepper, which is part of the identity commitment, then you'll the account that you'll derive is ultimately the different account, will ultimately be a different account, which sort of defeats the purpose because we want a stable account identity for the user across these accounts within this ecosystem of a user pool. And so thus the Pepper API, similar to the Prover API, will need to have an input in the request. And so we'll add a sort of similarly a skip odd check flag to the Pepper API. Additionally, the SDK will need to be able to support the ability to instantiate this. And so it'll just also similarly have a certain kind of parameter to trigger this mode when instantiating these accounts for keyless. And lastly, it's worthwhile to note that there aren't any changes to the validator code on the blockchain side. However, a framework upgrade will be required to install the new verifying key since a lot of the main logical changes are within the circuit, and to really have that be updated in the blockchain instead of any code changes in the validator. What we need to do is we need to make a update to the verifying key that's installed on chain and have the prover service use the corresponding proving key and generate proofs using that. here's a bunch of text that's copied over from the AIP, but the main risk is making sure that now that since we're providing an additional proving path, that these proofs are properly scoped such that proofs for these oddless accounts are able to be used for accounts that are supposed to be scoped to a specific application. Yeah, there's going to be circuit changes that are going to be required, and thus also a new ceremony, and that always has a lot of work that needs to be undergone to make sure that it's done securely and that it can be trusted. Additionally, we don't want developers to be misusing this functionality, because that would not be good when they're operating under certain assumptions under scope. So for example, if they wanted to use regular keyless accounts would never want to be able to use this proving path, as that means the keyless accounts that the users are signing into can be accessed by any other decentralized application, which could take malicious actions if they're able to do some social engineering to get the user to log in. So it's important for developer education and using the SDK to understand that when they're using this, that they're explicit about it. And this will be handled in the SDK, as the default behavior will be having these accounts scoped to the application, and will require the developer to explicitly enable this. Additionally, the verification key and the proving key will need an update, and there's always risks, and we've done a lot of work to try to make sure that the rotation of such keys are going to be as seamless as possible. But it will mean that all proofs that when these keys are rotated, all proofs that have already been generated by the old proofs, that old proving key, are implicitly invalidated, which means that all users that are logged in, it basically expires all their sessions, and they'll need to be able to log in. And this has some certain risks around potentially DDoSing our prover system, but there are ways to mitigate this and to scale this up, leveraging both the SDK and being able to anticipate such load. The main alternative solution to consider is, instead of supporting an additional proving path within the circuit logic, is to explicitly define an additional keyless public key type. We have a lot of infrastructure to support different public key types, which federated keyless also use, given that we have this abstraction of single key. So we could alternatively define a sort of a new oddless federated public key, where the ID commitment is a little bit different and doesn't contain the odd at all and isn't used to compute it, and so it's not used in part of its scope. And this would have the advantage of sort of this explicit type safety, that instead of it being sort of implicitly hidden within the notion of the ID commitment of the public key, that it's explicitly marked to the validator code that this is this type of account. However, there's a lot of drawbacks to this. That's one, it just adds an additional public key type, which if it's avoidable, it's kind of cleaner to not proliferate a whole bunch of different public key types. But most importantly, there's a lot of code changes involved on the validator side. That's also an additional drawback. But the biggest one is that the fact that this means that this would be a fundamental change in the way of the ZK relation, that we wouldn't be able to potentially use the same ZK relation. And that means that you would need to have an additional version of the circuit, which potentially would mean that you would need to be able to maintain simultaneously two versions of the circuit, two verifying keys, two proving keys, and so on. And so there's a tremendous amount of overhead in regards to that. Thus, if we're able to leverage the sort of existing design, or rather circuits, and the same Z correlation when it comes to the verifying and the verifying of the proofs. That has the yeah, it's highly preferable to do so to avoid such overrun. In terms of security, the primary concern, I think, is the ability to make sure that accounts are not being able to be properly accessed. So, for example, that proofs generated in this sort of skip odd check are only able to be used to verify these oddless accounts. And this is enforced via the keyless public key, which the ID commitment is used in the verification of the proofs. And so since in this oddless mode, the odd that is used to the odd value is set to the empty string, and that's used to calculate the IDC, that effectively makes it so that the scope of such proofs are limited to such accounts that are in oddless mode. So proofs that are generated in skip odd check are only able to be used to verify its appropriate oddless account, and vice versa. When the skip check odd check is disabled, that it can only be used to verify transactions appropriately. Other concerns is, any kind of bugs that can arise in circuit implementation that can also have the impact of potential unauthorized account access. Circuit development is done in a language called Circom, which is notoriously difficult to do and kind of tricky to review and write sane code in. And then additionally, as mentioned earlier, that it requires a trusted setup, that there's a lot of due diligence that has to be done to make sure that we do that properly and with enough trusted parties such that we can suss the new proving key and verification key that's generated from it. This outlines sort of the test plan, making sure that our circuit has the appropriate unit test to handle such new logic, unit tests in the SDK, and end-to-end tests in the SDK to that sort of test for the end-to-end functionality of this in steps 2 and 3. In step 4, we can also add an additional smoke test on the Rust side of the code that tests the validation path using one such proof of a proof generated from the new version of the circuit. And then lastly, making sure that we have unit tests on both the prepper and the prover, such that this skip odd check is only used for JWTs that come from OIDC providers that support such functionality. There's a world in the prover service where we potentially decentralize these services, and then we might not be able to necessarily enforce this, as we might have an ecosystem of provers, and the only service that's able to be used to generate proofs won't be our own. But we want to be able to, for now, when we have when sort of the pepper and proving capabilities are still centralized, we want to make sure that or at least when we are providing primarily the pepper service and the prover service, we want to make sure that it's limited to these providers to just hedge against potential misuse. In terms of backwards compatibility, it will maintain all the same backwards, all your existing federated keyless accounts, and keyless accounts will be, there won't be any issues there. On the validator side, there's no code changes, and on the circuit side, it's just introducing a new proving path of logic. And that's it for AIP 108.
Awesome. Thank you so much. There's a question about pepper service odd list queries being limited by ISS.
Yeah, I guess I wasn't seeing the chats, but yeah, that was covered sort of here implicitly to making sure that it's tested such that it is limited to the OADC providers that support such functionality, which is essentially the same as limiting it by ISS. Any other questions?
I have
This,
a question.
AI, yeah,
Is the
yes, Morgan.
AUD set by the developer?
No, the AUD is set by the identity provider. So in the federated case, it's Auth0 and Cognito. So for example, the AUD for an Auth0 might look like, www.auth0.com/ Disney plus maybe some kind of identifier that they might use internally. So it's provided by the identity provider, and you don't generally get to choose what it is.
Okay, thank you.
One question, and who sets the skip AUD check? It's a private input in CK circuit, or?
Yeah, it's a private input, but it's not a true private input in the ZK relations like some of the other inputs here. For example, like the UID val and the UID key, which in theory is like sensitive information like the email and such. This is just a input that is set by the prover itself, which uses the proving key. But by proxy, it's essentially controlled by the developer. They can decide to set it or not. And if they decide to set it, then it just means that now these accounts are not limited in scope by the odd, which refers to the application.
Makes sense.
Well, any other questions? Okay. Thanks for tuning into that. I know that's some parts might require a lot of prior knowledge of keyless systems, so please be sure to check out some of the AIPs. I think it's 61 and 90 something, or I forget what it is, but there's a lot more information that you can look. Yeah, 96 to get more familiar with some of the background things for things that might have been a little bit more opaque. All right, thank you.
All right. Thank you, Oliver. Thank you, George, for presenting. Just as part of the closing, I understand that like hopping on Zoom, needing to register might be a bit of a lift. So we'll work on improving that for our January and future sessions. I also wanted to note that all of these recordings are going to hopefully be uploaded onto YouTube before February. And so going forward, once you go to the AIP page, anyone will be able to access the presentation and recordings going forward. Awesome. Thank you all for being here. I look forward to our January session. Thank you. Bye.
Thank you. Bye, everybody.